Okay, let's begin. So we have seen yesterday that an L theory is categorical, or now what is called absolutely categorical, if it has only one model up to isomorphism. Yeah, that was the original definition of Veblen. However, thanks to Löwenheim-Skolem, his dreams were never to be realized. Because if a theory has an infinite model, then it has a model of every cardinality bigger equal the size of the language. Okay, every infinite cardinality bigger equal the size of language, thanks to Löwenheim-Skolem theorem. So then we started looking at some weaker version of categoricity, and which is the most appropriate one. So we say that an L theory is kappa categorical for a cardinal kappa bigger equal size of L, infinite cardinal, if any two models of gamma with size kappa are isomorphic. And we looked at some examples. So the theory of real vector spaces is indeed kappa categorical for every kappa bigger than the size of the field, because every vector space of size kappa has a kappa bigger than 2 to the aleph naught, has a basis of the same size, and whenever two vector spaces have same size basis, then they are isomorphic. So therefore this one works. Then obviously gamma inf set, the theory of infinite sets in the empty language L set, that is kappa categorical for every infinite kappa, obviously, because there is only one set up to isomorphism, and here I mean without loss we are assuming axiom of choice. Otherwise this statement wouldn't be true, because thanks to axiom of choice every set has a cardinality, every set is in bijection, it can be well ordered, so therefore you can find the least ordinal with which it is in bijection, and therefore you can define the cardinality. So well ordering theorem or equivalently axiom of choice is being assumed, and we have been doing that since we started with like more advanced parts of logic anyway, because we proved compactness theorem, that is a consequence of axiom of choice, it uses prime filter theorem. Okay, then yesterday we also showed an interesting result for dense linear orders, that if your dense linear order is unbounded, then Cantor isomorphism theorem, or which is also known as back and forth method, it shows you that this theory is aleph naught categorical, which means there is only one countable model up to isomorphism. Now just to add to this list, I am going to say something more. That's also a very interesting. Well, first let me define the language. So let's say this is the language of rings, which is F, G, H, C, E. That is what we have been using. This is a binary, unary, zero array, but I am going to interpret F and G as meet and join, and H as complement, and C and E as 0 and 1, the top, bottom and top element. So now I take the theory not of just Boolean algebras, but atomless Boolean algebras. Okay, so atomless Boolean algebras, do you remember? Do you remember any example of atomless Boolean algebras? Propositional logic provides one example. Can you be more specific? Chain. Chain is not an example of a Boolean algebra unless it is only two element chain. Say something more. Lindenbaum-Tarski algebra, yes, for a countably infinite language, yes, that is definitely. So, LT algebra for a countably infinite propositional language. What was our notation? We used BL, yeah. So BL, but size omega, yeah, I mean size aleph naught. So this is an example, but in fact this theory is aleph naught categorical. Okay. So what do I mean by that? That there is only one countably infinite model up to isomorphism. So this is the only atomless Boolean algebra which is countably infinite. And how do you prove something like that? If you remember, yesterday we saw something about this Cantor isomorphism theorem. What was given to you? That, I mean, even if, let's say, DLO and bounded, yeah, there are two dense linear orders which are bounded and contain at least two elements. Yeah, so suppose that is given to you. Then you map the least element to least element, largest element to largest element, and then in between you can play around just like this unbounded case. You can map any element to any element, and then below that there is a non-minimal element, above that there is a non-maximal element, and between any two elements there is a, thanks to density. Now if you remember, there was an exam question about density of atomless Boolean algebras, right. So atomless means that below any non-zero element there is another non-zero element. So that is like unbounded below. Okay, you will map 0 to 0, 1 to 1, but removing 0 and 1, it is unbounded below, it is unbounded above, and it is also dense. So using these properties, if you can list all the elements of one Boolean algebra, one countably infinite atomless Boolean algebra and another countably infinite atomless Boolean algebra, then you can just follow the back and forth method. You have to simply make sure that meets will get mapped to meets, joins will get mapped to joins. Yeah, there is slightly more work to do, but you can ultimately get there, and therefore by a same argument, essentially the same argument, you can prove that this is the only countably infinite atomless Boolean algebra. So as soon as you have density and all, yeah, everything starts working fine. Density and unboundedness. Any questions? Yes, the idea is still the same. Another thing which might be interesting for you, yeah, so now I am going to talk about L-ORD. Do you remember what it consists of? One relation symbol which is binary. Okay. And we saw that one of the examples is, I mean the simplest possible example is directed graphs, but I can also talk about graphs. They don't have to be directed. What is a graph? Do you remember the definition of a graph? What should you put in this theory? Simple graphs are, there are two properties, irreflexive and symmetric. Very good. So simple graphs, so I am going to take theory of simple graphs. Okay, so this is irreflexive plus symmetric binary relation. So this is the definition, but I am going to add something more to it. Okay, so for every single graph, so for example I am giving you this, okay, just this collection. This is a graph, this is a simple graph. How many vertices does it have? 3. Okay. Now, can you write down a sentence which says that a subgraph of my graph is isomorphic to this? The induced subgraph is isomorphic to this. Induced subgraph is isomorphic. What does that mean? I have some graph and it has 3 vertices. If I restrict to only those 3 vertices, then the graph will look exactly like this. So, what should I write down? There exists W1, W2, W3 such that R, W1, W2, very good, R, W2, W3 and not R, W1, W3. Do you understand this? What does this say? This says that there is, let me call this G equal to VE, vertex and edge set. So this sentence says that, let me call this phi G. So phi G says that there is, like G is an induced subgraph. G is isomorphic to, maybe I should be precise, is isomorphic to an induced subgraph. Okay, so every single finite graph can be written like this. Definitely, every single finite graph will have a corresponding sentence phi G. So, what if I say random simple graph? This consists of, gamma simple graph union phi G such that G is a finite simple graph. So, what am I claiming? I am claiming that there is, first of all I am claiming that this theory is satisfiable. Okay, first try to understand what it's saying. This is satisfiable means that there is a graph which has one copy of a given finite simple graph as an induced subgraph, and this should happen for any finite simple graph. So obviously you can imagine this structure, if it is satisfiable, then it must have an infinite model. Correct? Because the size of these finite graphs can grow larger and larger and larger. So therefore, if it is satisfiable, then it must be infinite. Now, how do you show this is satisfiable? Compactness. You choose the theory of simple graphs, that much you should always retain, it's just 2 sentences. And then you should add phi G for finitely many of them. Well, do you know any such example? If there are only finitely many such graphs, then you take disjoint union of all such, and then that's a model of that finite subset. So therefore, this is finitely satisfiable. So by compactness, this is satisfiable. And by Leeuwenheim's-Kolem theorem, it must have a countable model, because the language is singleton. So the smallest infinite cardinal bigger equal size of language is aleph naught. Okay, so I said lot of things. So this must have an infinite model of size aleph naught. Okay, So thanks to compactness, we know this exists. So this one is called a random graph. Yeah? Why is it called a random graph? So basically, you start with a countably infinite set of vertices. Yeah, let me draw some picture for you. And then, so random graph. You start with countably infinite set of vertices, and between any two vertices, if you want to put whether you want to add an edge or not, you decide that by doing a coin toss. Okay? If it is heads, I will put an edge. If it is tails, if it is a fair coin, yeah, then however I construct this graph, and you have to do it for every single pair. So that's why it's called a random graph. And how many such random graphs are there? Countably infinite random graphs. Well, I am writing it as the fifth example. So you can guess there is only one up to isomorphism. Okay. So this depends on coin toss. You have a question? Okay. So there is only one such random graph, and how do you prove that there is only one such random graph? The idea is very simple. Back and forth method. There is no other argument that you know. Okay, so you start by mapping any vertex to any other vertex. Then you look at its, now you choose another vertex, and now you look at the subgraph generated by those two. Yeah? Now that subgraph is finite. So you must be able to find, by appropriate choice of capital G, you must be able to find such induced subgraph in this model. And then you keep on building and building, and you will get an isomorphism using back and forth method.
What if you chose one isolated point and then other vertexes like
You have to be a little bit more careful, but back and forth method works. Okay, let's not go into details. So I am giving you all sorts of examples of how logic can be helpful in ordinary mathematics, pure mathematics. Yeah, we have seen one example of hyperreals, which is analysis. Yeah, this is graph theory. This is Boolean algebras. We have been talking about algebraically closed fields. So algebra is there. Yeah, everything can be done with appropriate choice of languages and theories. Okay, so yes, one more thing I think we also wrote. Did we write this? Gamma ACF 0 is kappa categorical for kappa bigger than aleph naught. Well, actually, if you observe all these examples, yeah, then if you cross a certain threshold, then we are saying it's kappa categorical for all kappa bigger than a certain threshold. Is that a coincidence? The behavior is very different for aleph naught, or in this case real numbers, the cardinality of real numbers, the behavior is different. I mean, how many vector spaces are there up to isomorphism of cardinality same as real numbers? R, R square, R cube. So for each non-zero natural number as dimension, you have a different one. right? So the behavior was different for the cardinality of real numbers. But if you cross that, then the behavior is identical. Similarly here, yeah, the behavior is, yes, here, atomless Boolean algebras, it is Aleph not categorical, but it is not categorical for uncountable cardinals. Similarly, this is Aleph not categorical, but it is not uncountably categorical. Yeah, for example, real numbers are a model of this, right? Real numbers are dense, rational numbers are dense, right? So you can actually play around with things. Okay, but perhaps I shouldn't say more. If you remember Dedekind cuts, yeah, then using Dedekind cuts you can say certain things over here, because Dedekind cuts, I mean, they materialize, they realize in real numbers, but they don't realize in rational numbers. Yeah, because in rational numbers there are gaps, in real numbers there are no gaps. So that way the behavior of reals and rationals is different. They are not in the same cardinality, but I am trying to provide you with one model of real of this theory, which is not isomorphic to real numbers. So what you do, you take real numbers plus a single vertex, single point plus a copy of rational numbers. Okay, that is a model of this, but it is not isomorphic to real numbers. It has the same size, but it is not isomorphic. Okay, that's because of Dedekind cuts. So my main point is that there is a very fixed cardinality, which is the size of language plus Aleph naught, this cardinality, and then all higher cardinals. So there is a clear distinction in behavior of this, and that's not a surprise. When people observed this, then one very prominent model theorist, logician, he proved this result. So that's called, and its proof is very hard. Morley categoricity theorem. So suppose kappa is bigger than size of L plus Aleph naught. If gamma is an L theory, that is kappa categorical, then gamma is lambda categorical for each lambda bigger than size of L plus Aleph naught. So the behavior is only different for this particular cardinal number, size of L plus Aleph naught. And if it is categorical for some kappa, then it is categorical for all kappa satisfying this cardinality condition. Yeah, this is a very deep theorem in model theory. And all the examples that we have seen definitely make this belief strong. Yeah, for example, this. I gave you some examples yesterday of countable models of this. Yeah, Q alg bar, then Q alg bar x, x1, x2, xn. You add some finite transcendence degree. Yeah, and then there are different non-isomorphic, pairwise non-isomorphic models. Any questions about this? Okay, Now, perhaps we should come back to a simpler question. So, we have shown that if a theory has model which is finite, then if a complete theory has a finite model, then every model of that theory has the same size. Okay, but I think we also mentioned something about the converse, a test for completeness. You remember that? It's called Wash-Watt test. So let us quickly state and prove this. If gamma is an L theory without any finite model, and gamma is kappa categorical for some kappa bigger equal aleph naught plus size of L, then gamma is complete. What is our favorite method of proof in logic? Induction, yes, but the second most favorite. Induction cannot be used here. What will you induct on? Proof by contradiction. So we are going to do that. So suppose not. Suppose gamma is incomplete. Okay, so incomplete theory. Yeah, that's a prelude to tomorrow's lecture. Gödel's incompleteness theorems. Yeah, it's about incomplete theories. So suppose gamma is incomplete, then what can you say? It is incomplete, so it cannot decide about some sentence. Yeah, so then there is some phi such that gamma doesn't logically imply phi and gamma doesn't logically imply negation phi. Okay. So there was an exercise which we have done several times, like so then what can you say about this? Both of them are satisfiable. So let M1 be a model of gamma union negation infinity, negation phi, and M2 be a model of gamma union phi. So since gamma doesn't have a finite model, M1 and M2 are infinite. Now, using a combination of both Leeuwenheim-Skolem theorems, using LS theorems, there is a model N1 of theory of M1 such that size of N1 is equal to kappa. Theory of M1 is a satisfiable collection of sentences, right? So therefore we can get some n1 of size kappa, because you can go up and down, yeah, upward and downward Leeuwenhoek's-Coulomb theorems, they will guarantee existence of this. Okay. And similarly, N2 satisfying theory of M2 such that size of N2 is equal to kappa. Now observe, I am talking about theory of M1, which is the collection of sentences which are true in M1. So gamma is contained inside there. Yeah, so in particular, N1 satisfies gamma and it also satisfies negation phi, and N2 satisfies gamma and it satisfies phi. So N1 and N2 are both models of gamma, but one satisfies phi and another one satisfies negation phi. So can they be isomorphic? Therefore, N1 and N2 are models of gamma that are not isomorphic. Models of gamma with size kappa, and therefore what we have shown, therefore gamma is not kappa categorical. End of proof. We simply proved the contrapositive, and this is Wash-Watt test. Very simple proof. So using this, now you can conclude lots of things. Yeah, let me go back to this slide where we are looking at examples of categorical theories. So let us look at this. The theory of infinite vector spaces. Yeah, I mean this is important. I am not saying 0 is a real vector space. I don't want that. I want to say add an axiom which says that there exists a W such that W is not equal to 0. If I add that, then this theory is kappa categorical for any kappa. So it satisfies the hypothesis of Wash-Watt test. Look at this. It should be an L theory without any finite model. So I said that there is at least one non-zero element, and as soon as there is one non-zero element, I should have all its scalar multiples, so it becomes infinite. So therefore the theory of vector spaces without non-zero vector spaces or infinite vector spaces, that theory is kappa categorical and hence complete. Similarly, the theory of dense linear orders which are unbounded, that is Aleph not categorical. Can it have a finite model? No. So therefore it is also a complete theory. What if I talk about bounded dense linear orders? Then I should add the hypothesis that there are at least two elements, because by density, by two elements I can generate infinitely many of them. So the theory of bounded dense linear orders with at least two elements is also Aleph not categorical and hence complete. Right? Theory of atomless Boolean algebras, of course every atomless Boolean algebra has to be infinite. Yeah? So the theory of atomless Boolean algebras is also complete. Similarly, theory of random graphs is complete, and ACF0 is also complete. Similarly, ACFP is also complete for any prime P if you understand what is characteristic of a ring. So there are so many examples of complete theories. But yeah, I mean let me quickly say something. that for finite things it doesn't really work. One theory can have one finite model and another finite model of the same size, but they are not isomorphic. So for example, Z mod 2Z, we have seen this, then you can take its product with Z mod 2Z, and Z mod 4Z is another group. Both of them contain 4 elements, but they are not isomorphic. Okay, you consider 1 in Z mod 4Z, then how many times do you need to add 1 to itself to get 0? 4 times. 1 plus 1 plus 1 plus 1 is 4, 4 is 0 modulo 4Z. So therefore, there is one element of order 4 in that side, but every element on this side has order 2. Okay? So therefore, yeah, I mean it's pairs of 1 and zeros. 1 comma 1 is of order 2 because 1 comma 1 plus 1 comma 1 is 2 comma 2, which is 0 comma 0. This is called Klein-Fehr group. Fehr is 4 in German. Yeah, Klein was German, so he said it's Klein-Fehr group. I mean, he did not name it Klein-Fehr group, but okay, so there can be a theory which has a finite, 2 non-isomorphic finite models of same cardinality. Okay. All right. So now let us go ahead. I think I have said everything I wanted to say about this. Okay. Now we want to understand this. Let us go back to high school. Around 8th grade, you must have first heard of the term quadratic equation. 7th, 8th, yeah, I am older than you, so I don't know when you learnt it. So, how do you solve a quadratic equation? Huh? Which one? Completing the square, yes, fine. But I am going to ask you this. Suppose A, B and C are fixed coefficients. So, if I write AW square plus BW plus C equal to 0, and then I am asking you whether there is a real number, because you only knew at that time, you only knew real numbers. Yeah. So, whether there is a real number which satisfies this. Just the question whether there is one. I am not asking you to find it. Can you do it in terms of A, B and C? What is the answer? B square minus 4AC is bigger equal 0. Okay, so this is true if and only if B square minus 4AC is bigger equal 0. So, if I am talking about the ordered field of real numbers, then look at that side of the formula. Does it contain any quantifiers? No. So, that is a quantifier free formula which is logically equivalent to this modulo theory of real numbers. Okay, I mean this modulo theory of real numbers needs a little bit more explanation. So I can write it for you. See, it says that theory of real numbers witnesses that for all WA, WB, WC, there exists a W such that AWS square plus BWB plus WC equal to 0 if and only if WB square minus 4WA WC is bigger equal 0. So basically, the theory of real numbers witnesses that these two formulas are the same. So what we have said, that one formula with quantifiers, this one, is logically equivalent modulo the theory to a quantifier free formula. So if you can do it, so now let me write down the more technical term. So say that an L theory gamma eliminates quantifiers if for any formula phi x bar there exists a quantifier free formula psi x bar such that gamma witnesses that for all W bar, phi W bar and psi W bar are logically equivalent.
So there should be WA, W square plus W.
WA what?
Like there exists W such as WA, W square.
Oh, sorry. Yes, I made a mistake here. Thank you. Let me write it again. WA W square plus WBW plus WC equal to 0. Yeah. So a theory is said to eliminate quantifiers if for any formula there is a quantifier free formula which is logically equivalent to it. Okay. Now this is the process that, I mean, in general there is no recipe for this. Yeah, for eliminating quantifiers there is no recipe. There are some well practiced techniques, but they work only in special situations. But before we do this, let me remind you that every formula is logically equivalent to 1 in a particular form. What is that form called? The pre-next normal form. So pre-next normal form has all the quantifiers in the beginning. So this is simply a reminder that all quantifiers, yeah, Q W1 bar, Q W2 bar, I mean Q1 W1 bar, Q2 W2 bar and so on, QK WK bar, and then inside it is quantifier free. Now, if I want to eliminate the quantifiers, then I should first look at only this, just the last quantifier which is present there. And then if I can eliminate that, then I will go to a larger QK minus 1. Then I will eliminate that, then I will eliminate all from, so we open it up from the inside and then we get to outside. Is that clear? Yeah, we try to eliminate quantifiers from inside out. And what is the quantifier that we have chosen in our language? We always choose there exist and not for all, because for all is negation, there exists negation. So even if you can eliminate, yeah, just there exists, it's okay. Moreover, okay, now a quantifier free formula, in what format can we write that? A quantifier free formula, you remember from propositional logic, what is the normal form for that? DNF. Yeah, so the DNF also works here. Okay, so DNF always looks like this. Disjunction of conjunctions, and if there is a there exists outside, then actually if you remember we proved a logical equivalence that I can take it inside. This is logically equivalent to this. If you don't remember this, do it as an exercise. That disjunction and there exists you can swap. Okay. So therefore, now the whole process of eliminating quantifiers simply boils down to eliminating quantifiers from a conjunction of atomic formulas, conjunction of literals. So in this case, literals are either atomic formulas or their negations. Okay, so eliminating quantifier simply boils down to eliminating a quantifier from a conjunction of literals, finite conjunction of literals. Okay, first let us try to understand what this quantifier really means. So for example, yeah, I am writing down this particular equation which you all know, x square plus y square equal to 1. In real numbers, what is the definable set of this? It's a circle, yeah? You are all scared to say the circle now, yeah? But this is actually a formula and I am asking you what is the set defined by this. So, fine, this is a circle, I am going to draw a circle. What is the origin? 0, 0, and this point is 1, 0. Okay, good. Now I am asking, if I project onto the first component, which means I should write this. There exists a w such that x square plus w square is equal to 1. What are the values of x which satisfy this? What are the values of real numbers which satisfy this? Minus 1, it does satisfy. 0, 1, everything in between, everything in between. So this is satisfied, yeah, so the set defined by is the interval minus 1 to 1. Okay, so basically what I am doing, I am looking at a point, then I am drawing the vertical line at that point and I am asking whether this vertical line intersects the circle. If I draw a vertical line over here, does it intersect the circle? No. So therefore, that point is not in minus 1, 1, the closed interval. I mean the formula here is simple, right? It is minus 1 less equal x less equal 1. This is the formula, yeah, minus 1 is less equal x and x is less equal 1. So that's the formula. So what is the meaning, what is the geometric interpretation of there exist? It's projection. So geometric interpretation of there exist is projection. So if you are given a definable set, then you try to project it down to something smaller. You are studying linear algebra? Yeah, so in linear algebra, you solve systems of linear equations. Now those linear equations are finite conjunctions of atomic formulas. Yeah, because what are atomic formulas? In the case of real vector spaces, the language of real vector spaces. Some scalar multiples of some variables is equal to scalar multiples of constants. So ultimately you can rewrite it as a single linear equation, R linear equation, right? So that one you can project, and then you ask whether this particular system of linear equations has a solution. What are you doing? You are asking for there exists a W such that some system, some matrix equation, yeah, A bar, then usually you write W bar, Y bar, and you are asking for W bar and is equal to some B bar. This is what you are asking. Gaussian elimination method will let you solve this system of equations. Well, actually, if you work a little bit harder, you can show that gamma R vector spaces eliminates quantifiers. I mean, essentially, the argument is based on Gaussian elimination. So you are asking for projections of solution sets of linear systems to lower dimensions, and that projection is there exist. If you want a geometric interpretation of for all quantifier, universal quantifier, then this vertical line has to lie entirely inside the definable set. See, there exists says that the vertical green line, there is a point on the green line which is also on the definable set. For all says, for all points on the green vertical line, it is inside the definable set. So there is a lot of geometry hidden in these pictures. I will end this by giving you more, so this is usually called QE, yeah, quantifier elimination. QE is quantifier elimination. So some more examples of theories which admit quantifier elimination. So that is gamma SEF. Yeah, the theory of algebraically closed fields, it eliminates quantifiers. In algebraic geometry, this is a celebrated theorem. It's called Chevallier's theorem. I mean, in more technical terms, it says that the projection of any algebraic variety is a constructible set. Constructible set is a finite Boolean combination of algebraic varieties, and algebraic varieties are solution sets of polynomial equations. So this is the one. Then gamma RCF. Okay, real closed fields, which means the theory of real numbers as an ordered field. Okay, so this is called Tarski-Seidenberg theorem. Yeah, there are big names associated with this. Then similarly, you can show that theory of dense linear orders also eliminates quantifiers. Then theory of ordered abelian groups also eliminates quantifiers. Pressburger arithmetic, which is a weaker form of our normal arithmetic on natural numbers, that also eliminates quantifiers. And it has applications in computer science because you want to eliminate quantifiers fast enough. Yeah, so computer scientists are very heavy on this because decidability problems and algorithms, they all depend on how fast you can eliminate quantifiers. Okay. So yeah, with this I am going to end today's lecture.